We will start with our topic, that is stereochemistry. Now, stereochemistry is the branch of science which deals with the three-dimensional structure of molecule and their effect on physical and chemical properties is known as stereochemistry. To represent molecule as three-dimensional object, we need at least one carbon sp3 hybridized. We have given some examples over there. This is the central metal, this is the central atom that is bonded to four different groups. This is hydrogen, iodine, bromine and chlorine. But in stereochemistry we need 3D object, means the molecule must be presented in 3D view. This is the view is 2D, so it is not appropriate for stereochemistry. Now this molecule is denoted in 3D structure. The dark line is towards the observer and the dotted line is away from the observer. So this is the appropriate diagram which is represented in 3D view. Next are isomers. We are familiar with isomers in previous chapter. The different compounds which have the same molecular formula is known as isomers. Here we will learn the parts of the isomer, that is isomers are distinguished in constitutional isomers or structural isomers or stereoisomers. Now constitutional isomers are isomers differs in connectivity of their atoms or the structural atoms. Okay, the atoms will be same but the structural formula will be different. Stereoisomers, isomers with a different in 3D arrangement only. Now the stereoisomers are subdivided into conformational isomers and configurational isomers. What are conformational isomers? Isomers which are readily converted into each other through a single bond. And configurational isomers, no rotation possible through single bond. These configurational isomers are further subdivided into two groups, that are geometrical cis or trans isomers or optical isomers. Next is optical activity. Now what is optical activity? We know that ordinary lights are composed of rays of different wavelengths vibrating in the directions perpendicular to the path of its propagation. These vibrations can be made to occur in a single plane by passing ordinary light through the polarizing nickel prism. Such light whose vibrations occur in only one plane is called as plane polarized light. Here it is a light source, then light passes through the polarizer, and this is the sample tube and this is the analyzer. Here we are the observer. Okay, compounds which rotate the plane of polarized light are called optical active compounds, means optically active compound, and this property is known as optical activity. That is, rotation of plane of polarized light can be of two types. Okay, now we will see the types, that is dextrorotatory and levorotatory, which is denoted by d, small d or small l. Okay, dextrorotatory, if the compound rotates the plane of polarization to the right, means if it rotates to clockwise direction, it is said to be dextrorotatory. And if the compounds means if the compound rotates the plane of polarization light to the left, that is anti-clockwise, it is said to be levorotatory. The change in the angle of plane of polarization is known as optical rotation. The optical rotation is detected and measured by the instrument called polarimeter. Measurement of optical activity is reported in terms of specific rotation alpha, which is given as, see, this is the formula of specific rotation, which determines the optical activity. Alpha is specific rotation, T is temperature of measurement, that is over here, and lambda is wavelength of the light used, alpha is observed angle of rotation, L is length of sample tube in decimeter, C is concentration of the sample in gram per ml of solution. Next, chirality. The term chiral means it is used for both objects which have right-handed and left-handed forms, that is, molecules which have handedness, and the general property of handedness is termed chirality. An object which is not superimposable upon its mirror image is known as chiral. Okay, now see the hands. If we place a mirror over here and if we raise our hands like this in front of the mirror, and if we superimpose upon each other, then it is not superimposable. So the our hands, what are our hands? It is chiral molecule. Okay, now see this molecule over here, CXWZY. Okay, this is the mirror image exactly of it. And if we superimpose this molecule on this, these are both are non-superimposable mirror images, and so the molecules are said to be chiral. Okay, now what is achiral? Objects and molecules which are superimposable on their mirror images is achiral. Achiral molecule has internal plane of symmetry, a hypothetical plane which bisects an object or molecule into mirror reflective halves. An object or molecule with an internal plane of symmetry is achiral. This is this is a butterfly diagram, and if we draw a plane over here, the two parts are similar. Okay, this is one conditions that a molecule is achiral, and second one, it is the mirror image and it is superimposable on its mirror images. If we superimpose this butterfly on this, it will exactly be mirror, it is the mirror image and it is superimposable on it. Okay, means over here object and molecule which are superimposable on their mirror images is chiral. Chiral and achiral compounds, some examples are over there. Chiral asymmetric has 4 different atoms bonded to carbon. Achiral does not have 4 different atoms bonded to the carbon. If we see, this is the central metal, sorry, this is the central atom carbon, which is joined by two groups which are different and two are similar, so it is achiral. And over here the central carbon atom, is bonded to CH3 and Br, H and Cl, which are four different groups. Now look at here, chiral has four different groups bonded to the carbon atom. These are the four different groups bonded to the carbon atom, and this is a chiral carbon because it has only three groups. Now see this chiral with two chiral centers. These have two chiral. This whole group is one part, and this three groups are other part. Now here we will see the second carbon, that is C2. The whole group is bonded to other carbon and the other groups, and this one is bonded to other group. Okay, this is also, this have three chiral carbon centers, C1, C2 and C3. If you will observe that the C1 group is bonded to H, OH, CHO, and this whole group is a different group. Now C2, if you will observe, it is bonded to H, OH, this one is another group and this one is other group. Okay, now same as it is for C3, that OH is bonded to other, H is bonded to other, and this one is the whole group and CH2 is another group. Okay. Stereogenic center or stereocenter. A stereogenic center is defined as an atom on which an interchange of any two atoms or groups results in a new stereoisomers. When the new stereoisomers is an enantiomer, the stereocenter is called chiral center. All stereocenters are not tetrahedral. Let us see the example. This is the examples where the carbon atom is bonded to four different groups, that is COH, OH, CH3 and H. If we interchange between two groups, that is H and OH, we will get new isomers. First and seconds are enantiomers, non-super mirror images, impossible mirror images of each other. Hence the stereo center is a chiral center. Okay. Now stereogenic center is continued. We will continue with the second example, that is cis isomers. Cis means the groups are on same side, that is cis. Okay. Now we will interchange the two groups, that is example H and CH3, means one side we will change it. Now what we will find, that is CH3 CH, we get trans isomers, that is new stereo isomers. So third and fourth are not enantiomers, they are distereomers. Hence in this case stereo centers are not chiral center, also they are not tetrahedral. Stereogenic center or stereo center. Thus all chiral centers are stereo centers, but all stereo centers are not chiral centers. If a molecule contains only one chiral center, it must be chiral. Molecule containing two or more chiral centers may or may not be chiral. For example, mesotartaric acid. If we take the examples of mesotartaric, that is two chiral centers, but it is a chiral molecule. See, these are two chiral centers. It has a plane of symmetry, a chiral due to plane of symmetry. Why? The reason behind this is it has a plane of symmetry, so it is a chiral molecule. Now stereoisomers. Isomers having same molecular formula but different spatial arrangement of their atoms are known as stereoisomers, and stereoisomers are have two parts, that are enantiomers and distereomers. Stereomers, which are non-superimposable mirror images of each other, are called enantiomers. Chirality is the necessary and sufficient condition for existence of enantiomers. They always exist as discrete pairs. See, these are the mirror images of each other but are non-superimposable. These are the two isomers of lactic acids. These are enantiomers. Now these are the examples of distereomers. Let us see the definition. Stereomers that are not mirror images of each other are called distereomers. See, these are not the mirror images of each other. These are enantiomers, and this is also enantiomers. Okay, A, B, and C, D. These are four isomers of 3-bromo 2-butanol, and these are distereomers of each other because they are non-superimposable mirror images. Geometrical isomers. Geometrical isomers occurs as a result of restricted rotations about a carbon-carbon bond. This is also called cis-trans isomerism. This isomerism exists exhibit by variety of compounds such as compound containing double bond, that is carbon-carbon, carbon-nitrogen, and nitrogen-nitrogen double bonds. Compound containing cyclic structure or compound containing restricted rotation due to steric hindrance. This is cis isomers and this is trans isomers. Cis isomers and trans isomers. These are the examples which I have given over here. Now, what are conformational isomers? Conformational isomers are the isomers that can be converted into one another by rotation around a single bond. Example, eclipsed wedge and anti-butane are all conformational isomers of one another. Eclipse means that identical groups are all directly in the line with one another. Wedge means that identical groups are 60 degrees from one another, and anti means that identical groups are 180 degree from one another. See, these are eclipse form, antiform and gauche form. And in eclipse form, as I have given, that all groups are in line with one another. See, all groups are in line with one another. Now in antiform, the same groups are 180 degrees towards each other. Now the opposite groups are 180 degree, or the same groups are at 60-degree angles. These molecules can be interconverted by rotating around the central carbon-carbon single bond. Now flying wedge or wedge dash projection formula. We will see the projection formulae. The flying wedge projection is most widely used three-dimensional representation of a molecule on a two-dimensional surface, that is on two-dimensional paper. This kind of representation is usually done for molecule containing chiral center. In this type of representation, three types of lines are used. A solid wedge or thick line, it represents bond projecting towards the observer or above the plane of paper. If we consider a plane of paper, okay, then a thick line means that it is towards the observer, means it is above the plane of paper. The bond projection towards the observer or above the plane of paper. The continuous line or ordinary line means this one, it represents bond is in the plane of paper. A dash wedge or broken line, see this one, the broken line, it represents bond projecting away from the observer or below the plane of paper. Means the dotted lines I have said earlier, it is away from the observer, and the thick line, it is towards the observer. This is the ball and stick model of 3D structure of methane, as I have given over here, and this is the sketched 3D structural formula of methane. Now, Fischer projection formula. Fischer projection provide an easy way to draw three-dimensional molecule on two-dimensional paper, and all the bonds are drawn as solid lines around symmetric carbon atom. The Fischer rules for showing the arrangement around asymmetric carbon atom. The carbon chain of the compound is projected vertically with the most oxidized carbon at the top of the place, the carbon number 1 at the top as defined by the nomenclature rule. The chiral carbon atom lies in the plane of the paper and usually omitted. The intersection of cross lines represent asymmetric carbon. The horizontal bonds attached to the chiral carbon are considered to be above the plane of paper or point towards the observer. The vertical bonds attached to the chiral carbon are considered to be below the plane of paper or point away from the observer. See, these are the vertical bonds which are away from the observer, and these are the horizontal bonds attached which are above the plane and towards the observer. Now this, in general, we write the Fischer projection formula in this way on a plane of paper, but actual molecule will be like this. A Fischer projection, see over here, I have given the observer is over here. Now it is imagining the molecule. The horizontal lines are away from it and the vertical lines are towards it. Okay. Now this is the molecule glyceraldehyde. I have given the example over here. The lines which are horizontal are away from the observer, as I have said earlier. See over here, the horizontal bonds attached to the chiral carbon are considered to be above the plane of the paper, and these are the towards the observer. Okay, and vertical bonds are away from the observer. Horizontal bonds, see, horizontal bonds are towards the observer, This is the horizontal bonds are towards the observer, and it is represented as dotted lines, and this is the thick lines. Sawhorse projection formula. The Sawhorse formula indicates the arrangement of all the atoms or groups on two adjacent carbon atoms. The bonds between the two carbon atoms are drawn diagonally and of relatively greater length for the sake of clarity. The lower left hand carbon is taken as the front carbon or towards the observer, and the upper right hand carbon as the back carbon of the away from the observer. Example, ethane. This is here the observer is there, and if we observe the molecule from here, okay, the back carbon is away from the observer and the front carbon is towards the observer. Now this is the anti-molecule if the observer is seeing the molecule from here, and if the molecule is like this, it is in eclipsed form. This is eclipsed form, anti form, and this is quench form. That is the thick dot, black color dot is methyl group. All parallel bonds in Sawhorse projection formula are eclipsed, and all anti-parallel bonds are opposite or scattered. Wedge represent is that in which bulky groups are nearer to each other at 60-degree angles. Now Newman projection formula. Newman devised a very simple method of projecting three-dimensional formulas on two-dimensional paper, which are known as Newman projection formula. In this formula, the molecule is viewed from the front of along the axis of carbon-carbon bond. The carbon nearer to the eye is represented by a point and the carbon atom towards the rear by circle. See, this is represented by a point, it is towards us, and the back carbon is denoted by a circle. The three atoms or groups on the carbon atoms are shown as being bonded to dot or circle by an angle of 120 degree to each other. Now it is placed by 120 degree to each other. The Newman formula: all parallel bonds are eclipsed, or all anti-parallel or opposite bonds are staggered. Now this like this, if the molecules are in one line, it is eclipsed, and if the molecules are at 180 degree, it is anti, and if the molecules are at 60 degree, it is gauge formula. Now nomenclature, which is a D and L system of nomenclature. As if you are seeing the molecule over here, in short, what is the D series? If the OH molecule is on the right hand side, it is D, and if the OH molecule is on the left hand side, it is L, denoted by L in simple language. See, this nomenclature is mainly used in sugar chemistry or optically active polyhydric carbonyl compound. This is a relative nomenclature because all the configuration described with respect to glyceraldehydes. All sugars whose Fischer projection formula shows the OH group on the right hand side of the chiral atom belongs to the D series, and similarly if OH is on the left hand side, then the sugar belongs to the L series. Okay, as I have said, if the OH group is on right hand side, it is D series, and if the OH group is on left hand side, it is L series. See this example: D plus glyceraldehyde and L minus glyceraldehydes. See, the OH group is on right hand side, so D, and OH group is on left hand side, so it is L. It must be noted that there is no relation between sign of rotation and plus, minus or dl and configuration D and L of enantiomers. Any compound that can be prepared from or converted into D plus glyceraldehydes will belong to D series, and similarly any compound that can be prepared from or converted into L minus glyceraldehydes will belong to the L series. Erythro and trio compounds system of nomenclature. What is erythro? Erythro means the groups will be on same side, and trio means the groups will be of opposite sides. This is RCABCABR or RCAB and CBCR. That is, out of 6 substituents on 2 asymmetric carbon, at least one should be in both the carbons. When two like groups in picture projection formula are drawn on the same side of vertical line, the isomer is called erythroform. If these are placed on the opposite side, the isomer is known as cryoform. See, these are some examples of erythroform and cryoform. See, CH3H group is on same side, so it is erythro, and H groups are over here are on opposite sides, so it is trio. This again H group on same side, erythro and trio. Now the most important, R and S nomenclature. The order of rearrangement of 4 groups around a chiral carbon is called the absolute configuration around that atom. System which indicates absolute configuration was given by 3 chemists, that is R.S. Kahan, C.K. Ingold and V. Prelog. This system is known as R and S system or the Kahan-Ingold-Prelog system. The letter R comes from the Latin rectus, meaning right, while S comes from Latin sinister, means left. Any chiral carbon atoms have either an R configuration or a S configuration. Therefore, one enantiomer is R and other is S. A racemic mixture may be designated as R and S, meaning a mixture of two. The RS nomenclature involves 2 steps. Step 1. The 4 ligands, atoms or groups attached to the chiral center are assigned a sequence of priority according to the sequence rule. Means the 4 groups, which atoms or groups which will be attached to a carbon atom in the chiral center will be given a priority, that is a sequence rule it is known as. Now rule number 1. If all the 4 atoms directly attached to the carbon atom are different, priority depends on their atomic number. The atom having highest atomic number gets the highest priority, that is number 1. The atom with lowest atomic number is given lowest priority, that is number 2. The group with next higher atomic number is given the next higher priority, 3, and so on. For example, if we consider this example, then the increasing atomic number is 4, 3, 2, 1. Okay. Fluorine will be at number 4, chlorine will be at number 3, bromine will be at number 2, and number 1 will be iodine. This is the increasing priority. Okay. Now rule number 2. If 2 or more than 2 isotopes of the same elements are present, the isotopes of higher mass receive the higher priority. If there are isotopes in this molecule, then the increasing priority will be in this way. Okay. Rule number 3. If 2 or more of the atoms directly bonded to the chiral carbon are identical, the atom number of the next atom is used for priority assignment. If these atoms are also having identical atoms attached to them, priority is determined at the first point of the difference along the chain. The atom that has attached to it an atom of higher priority gets the higher priority. Okay, now see what this means. If it is attached to 2H and C, here it is attached to CH2 and CH2, but here are 2 hydrogens, here are 2 hydrogens, and here are also 2 hydrogens, but this is attached to Br, okay, the highest group, so it will be given as second priority, and it is attached to carbon, okay, but here also it is attached to carbon. Now there is a confusion between these two things. Now what we will see the next atom which is attached to it. Now here the next atom is attached, it is always also a carbon, but over here it is attached to an iodine. Now what will happen, we will give this group the third priority. Over here see, we have given the third priority, and this group will be given as fourth priority, means first, second, third, fourth. In the above example, the atoms connected directly to the chiral carbon are iodine and the three carbons. Iodine has the highest priority. Connectivity of other three carbons are 2H and Br, 2H and C, and 2H and C. Bromine has the highest atomic number amongst CH-Br, and thus CH2-Br has highest priority among these three groups, that is priority number second. The remaining two carbon are still identical, C and 2H. Connected to the second carbon of these groups are 2H and I, and 2H and C. Iodine has the highest priority amongst these atoms, so that CH2CH2I is next in priority list, and CH2CH2CH3 has the third priority. Rule number 4. If a double or a triple bond is linked to chiral center, the involved electrons are duplicated or triplicated. See, these are the examples. Now, if there is a double bond or a triple bond over here, okay, the molecules, what we will do, it will be duplicated or triplicated, means we will take it 3 times and we will count it as 2 times. But this rule we obtained the following priority sequence. Now this is the sequence, increasing sequence of the molecule. Step number 2. The molecule is then visualized so that the group of lowest priority 4 is directed away from the observer. At this position, the lowest priority is at the bottom of the plane. What will happen? The lowest priority number will be at the bottom of the plane and it will be away from the observer. If the eye travels clockwise, as we look from the group of highest priority to the group of second and third priority, means if our eyes go in clockwise direction from 1, 2 and 3, this way, 1, 2 and 3 clockwise arrangement, then it is R configuration. And if our eyes go through 1, 2 and 3 in anti-clockwise arrangement, that is S configuration. Let us apply the whole sequence to bromochlorofluoromethane. See this molecule. Okay. Now which is the highest priority over here? Bromine will be highest priority. Then it will be chlorine. Then it will be fluorine, and then it will be hydrogen. Okay. Hydrogen is away from the observer because it has number 4. Priority number 4. Now we will observe from first, second and third. Okay, so the molecule is S configuration because it is going right way, like anti-clockwise direction. In the Fisher, the least priority number is not at the bottom of the plane. In such cases, the Fisher projection formula of the compound is converted into another equivalent projection formula in such a manner that atom the lowest priority is placed vertically downward. This may be drawn by the two interchange between 4 priority numbers. The first interchange involves the two priority numbers. One is the least priority number and the other is priority number which is present at the bottom of the plane. In the above case, first interchange will take place between 2 and 4. Now we will interchange the above example's priority. Okay, this was its priority 1, 2, 3 and 4. We will interchange it. Okay, now the fourth number will go down, second number will come over here, first and second will remain as it is, and now we will number it. A second interchange creates the original molecule, that is A. This was your molecule which we have interchanged. Now second interchange between the remaining group, that is 1 and 3. Okay, now we will interchange it 1 and 3. This is the priority loop. According to 1, 2, 3 are clockwise, hence configuration is R. Now example CHO, CH2OH, H and OH. First interchange between 3 and 4. We will interchange these groups, that is 3 and 4. Second interchange will be 1 and 2. So it is a clockwise, hence the configuration is R configuration. We have to interchange the atoms that we can get the right configuration. This is stereochemistry. It is little bit tricky regarding your imaginations. So we have to interchange. If you will see this object, your eyes will go right likewise. So you will see that it is S configuration, but when we will interchange the group, we will get the R configuration. An odd number of interchange of positions of groups on chiral carbon gives different compound. An even number of interchange of positions of groups on chiral carbon gives same compounds. An alternate, simple and most widely accepted procedure used now is applying 1982 to assign R-S configuration. In the case of Fischer projection is as follows. Now case 1, R and S nomenclature from Fischer projection formula. It is also known as the golden rule. In a Fischer projection, the group of lowest priority 4 is on a vertical line. Means it is on vertical line. Then the assignment of configuration is R for a clockwise sequence of 1 to 2 to 3 and S for the anti-clockwise sequence. See, for example, over here, this is fourth priority, this is first, second, third. Now we will have given the first, second, third and fourth priority. Now we will interchange what 1, 2 and 3 likewise. This is anti-clockwise, so it is S configuration. However, if the group of lowest priority is on horizontal line, then the assignment of configuration is S for a clockwise sequence of 1 to 2 to 3 and R for the anti-clockwise sequence. Now this group is of higher priority because O is attached directly to carbon, and this is of second priority, this is third and this is fourth. Now first, second, third, okay, we are going like this in anti-clockwise direction. So it is, but lowest priority at horizontal line means the lowest priority order is on horizontal line, so it is R configuration. Actually it is moving anti-clockwise. Now here are some examples when molecule contain two or more chiral centers. Each chiral center is assigned an R or S configuration according to the sequence and conversion rule. Thus plus tartaric acid is 2R and 3R, and over here carbon number second and third. Okay, this is both are C2 is R configuration and this is R configuration. Okay, configuration at chiral carbon second. If you will consider the second molecule, that is C2, the first priority order is 1, 2, 3 and this is 4. Okay, now we will go likewise. It is anti-clockwise, but the lowest priority order is on horizontal line, so it is R configuration. Now if we will observe C3, the first is over here 1, second is over here 2 and third is over here. It is also an anti-clockwise direction, but the lowest priority order group, that is hydrogen, is on horizontal line, so it is R configuration. RNS nomenclature, that is case 2, that is flying wedge formula. In the group of the lowest priority is away from the observer, that is bonded by dashed line, and the priority sequence 1, 2, 3 is clockwise, then the configuration is assigned as R. If the priority sequence is anti-clockwise, then the configuration is S. I have given the example over here. Lowest priority order is on the dashed line. Okay, the dashed line over here, and first over here, first number, this is second number, and this is third number. Okay, now how it is going? It is going in clockwise arrangement, thus the configuration is R configuration. If the group of lowest priority is not bonded by dashed line, then interchange a pair of groups so that the group with the lowest priority is bonded by dashed line. Now see the sequence 1, 2 and 3. If it is, now see the sequence 1, 2 and 3. If it is clockwise, then the configuration is assigned as S, and if the anti-clockwise, then R. This is because you have interchanged a pair of group and now you are determining the configuration of enantiomers of original molecule. See, this is the least priority order is not bonded with dashed line. This is not least priority order. We have to interchange it. When we will interchange, and this is third position and this is fourth position, this is R configuration, which means that the original compound has S configuration. Means original compound has S, and this is R configuration by interchanging the molecule. Now this is the end of our chapter. I hope you understand, and if there are any queries,